Hi, I'm Nikos.
Hi, I'm Konstantinos, and today we're going to talk to you about PaSh, a data parallel system for the shell.
Shell scripts are everywhere because the shell is everywhere. It is the default system interface, even in environments that do not contain other programming languages. It's a universal composition environment that allows the composition of programs that are written in any programming language. This allows really succinct program composition for data processing or system administration. To explain the basics of Unix pipelines, we'll show you a classic example. Given an input document, how to compute the top n, where n could be 5, words and their counts. In Unix, you can express the solution to this problem using a single line Unix pipeline. The first stage, tr, converts any non-alphanumeric character to a new line character. The next stage converts everything into a lowercase character. The stage after that sorts words in the stream so that identical words end up being next to each other. The next stage eliminates any duplicates and counts the repetition. The last but one stage sorts all these counts in reverse numerical order, and the last stage outputs only the number of lines necessary, in our case 5. This works great if we have one input file, but how would it work if we had hundreds of files? It would take a long time to process the input. Parallelizing Unix shell scripts is not trivial. It requires considerable manual effort. One option would be to use command-specific flags made available by the developers of individual commands. Another option would be to use restricted parallelization tools, but we would need to take care of the correctness of the resulting parallel script. And finally, we could rewrite everything in a parallel framework, particularly tailored for this class of computation, such as MapReduce. But of course, this would no longer be the shell. Why is automated shell script parallelization so difficult? First, even if we look at an individual command, it may be written in any of many programming languages, so it's not amenable to a single analysis. In several cases, a completely opaque black box. On top of that, the shell language primitives provide additional constraints that have to be taken into account. And finally, there is some runtime support necessary for hooking things together, making sure the results are correct, accelerating the computation, and other issues. We have developed a system called PaSh that solves these challenges and offers mostly automated parallelization of Unix shell scripts. Suppose you have a shell script like the one on the left. The first thing that PaSh does is parse a script to create an abstract syntax tree, and then it attempts to compile this abstract syntax tree into a data flow intermediate representation. It then applies several transformations iteratively, depending on key information about these commands. Next, it generates the parallel script that is ready for execution. Today, we will discuss three components in detail. The first is the annotation language that provides key properties about the parallelizability of individual commands. Second, the data flow model and associated transformations. And third, selective components from the runtime library. Let's start with the annotations. We conducted an extensive parallelizability study across individual Unix commands and designed an annotation language for extensibility purposes. Now, the average Linux path contains thousands of commands, so we wouldn't be able to study and characterize all of them. Instead, we opted for two smaller but representative and widely used sets of commands. The first is the POSIX set, available on every major Unix system, such as BSD, Linux, and Mac OS. The second is the GNU Core Utility Library, installed by default on any GNU Linux system and available for other systems. Studying the commands in these sets, we devised 4 broad parallelizability classes. Rather than describing a command's full observable behavior, these classes focus on key information that's important for data parallelism. There are lots of interesting details here, like the interaction between flags and the order of input consumption that you will have to read in the paper. This study led to the design of a small domain-specific language for annotating commands. This language essentially defines a bidirectional correspondence framework between commands and nodes in the data flow model. They effectively instruct PaSh on how to translate a command instance to a data flow node, but also back from the parallel data flow graph to the parallel shell script. In turn, we use this parallelizability DSL to annotate commands in POSIX, GNU Core Util, as well as commands found in the wild. Let's take a quick look at the 4 command parallelizability classes. The first class is stateless commands. These operate on individual lines of input, which is the key element of a Unix data stream, and their results can be combined using concatenation. For example, the tr command that is used to convert uppercase characters to lowercase characters can be concatenated to give us a result that's equivalent to sequential execution. These commands are trivially parallelizable. The next class is parallelizable pure commands that maintain some state across lines of input. These commands can also be parallelized, but we have to be careful when combining the partial results to account for the internal state. The third class is non-parallelizable pure commands. These commands are still pure in the sense that they do not have external side effects, but their internal state cannot be trivially combined. Finally, we have side effectful commands, such as move or cp, which have side effects and are clearly not parallelizable. The class of side effectful commands is the largest because of how central the file abstraction is in Unix.
So let's now move to the second contribution of our work, which is the data flow model and the corresponding transformations. So, as we mentioned in the challenges, the shell language enforces dependencies and scheduling constraints that the parallelizing compiler needs to be aware of. So in this case, the first cut needs to execute before the second cut due to this semicolon here. Therefore, PaSh's compiler frontend first identifies all regions of the code that do not have any scheduling constraints and transforms each one of them into a data flow graph. For example, in this case, we would have two data flow graphs, and let's look at the first one. As you can see, there's cat, a processing node of the data flow graph that reads from two inputs, F1 and F2, and then writes to out.txt. The semantics of the graph of data flow graphs in our model is that they have no scheduling constraints, so all nodes of them in them execute concurrently, communicating with channels that behave exactly as Unix FIFOs. And each data flow graph takes as input a set of input files and writes to a set of output files, possibly including its standard input and standard output. The important thing to note is that each data flow graph does not do any other side effect on the environment. Here, similarly, the second data flow graph would be this. The cat reads from out and then writes to its standard output. So let's now focus on a slightly more complex pipeline that is only one data flow graph, so that we can look at the transformations that PaSh performs. And note that all of the transformations that PaSh performs are semantics preserving. So given the semantics of the input files and the output files, PaSh will perform transformations that will ensure that the output, so the output files of the transformed data flow graph will be exactly the same as the original ones. So let's look at the first. So this is our pipeline here. So as you can see, there is cat that reads from F1 and F2, writes to tr, writes to sort, which then writes to out.txt. And let's look at the first transformation that we could do. So first, we could actually parallelize tr by splitting its input and then merging its output using a cat. And this we can actually do because tr is stateless, which is something that we know from the correspondence framework. So after that, we can apply a second transformation that removes a cat followed by a split that has where the cat has the same number of inputs as the split has outputs. So in this case, by removing those two, we get that F1, the first TR reads directly from F1 and the second TR reads directly from F2, getting rid of this unnecessary merging and splitting. Similarly, we can perform a parallelization transformation on sort now. So the transformation on sort splits the input of sort into two, parallelizes sort, and then merges the output with a merge that merges sorted inputs, as in the merge sort algorithm. And this transformation we can actually perform because sort is known by the correspondence framework to be a parallelizable pure command where its aggregator is a merge. Finally, we can remove these two unnecessary merging and splitting here because they have the same number of inputs and outputs, and then we get this final graph, which is saturated in a sense, because it which is saturated in a sense, and we have that tr reads from F1, which then writes to sort, which merges, which writes to merge, and similarly F2, tr reads from F2, which writes to sort, and then the merge takes the outputs and produces out.txt. In our paper, we have the transformations that we showed here, and we give a lot more details about them. So if you want more details, you can read the full paper.
Let's switch to PaSh's runtime system. PaSh's runtime support solves several challenges, a few of which I'm going to outline below. These challenges are related to performance and correctness characteristics of the parallel scripts. The first problem is that Unix pipes are lazy. Writing to a pipe blocks if no consumer is reading, as the pipe does not have adequate buffering. Such blocking is unavoidable, as there will always be an aggregator node at some point up to the end of the parallel data flow graph to ensure results are equivalent to the sequential execution. 2, Unix makes command termination notification challenging, which can cause deadlocks. And 3, parallelizable pure commands, as we saw earlier, require careful aggregation. We'll focus on the first problem. Details about these and other problems are in the paper. Consider the parallel grep program on the left. It's a result of PaSh's compilation process. The problem with this program is that cat will first read from the first input stream up to completion, and then will start reading from the second stream. That means that the second grep will block until the first grep completes. A possible but inadequate solution would be to use intermediary files. This solution would allow the two grep commands to proceed in a data parallel fashion at the cost of pipeline parallelism. PaSh's runtime support solves this problem by offering a buffering primitive that pulls incoming streams eagerly, thus allowing upstream commands to execute in parallel. Eager is a normal Unix command available outside of the PaSh context and is designed in a way that fits into the data flow model.
Great. So let's now look at the demo, figure out how does it look like running PaSh on a real shell script. So to start, we'll show the shell script that we showed in the beginning of the presentation. This shell script has the pipeline that finds the top 100 words in a piece of text. And before that, it exports this input variable pointing at this input file. Note that this export has to be run before the script itself for this to work. So let's first set this input to be 100 megabytes. And let's run the script with PaSh and see what is the output that we get.
One eternity later.
Great. It took 43 seconds. So let's try running the same thing with PaSh, where with PaSh and width2, where we keep the output of PaSh on this separate file. Amazing. It took 29 seconds. So let's now run this. Let's first of all look at whether the outputs of these two are the same, and they are actually the same. So let's now look at what happens if we run PaSh with 4, but also if we write its debug logging output in a log, so that we can see what actually happens under the hood. So as you can see, this is even faster. It took just 19 seconds. Wow. And so let's now look at the log. So the log, first of all, at the top, it contains, it prints out some debugging information like all of the arguments that PaSh was called with. And then it goes into its compilation phase. And note that PaSh, exactly because export needs to run before the pipeline, and as we said, this is a scheduling constraint that's enforced by the shell language, it first just tries to compile the export command. But then it finds that it's actually a side effectful command, and therefore it runs the original command without modifying it. Then it targets the pipeline and tries to compile that, and it actually succeeds. And here is the output script that it produces. So first, it removes and recreates FIFOs for the parallel data flow graph for the communication to happen, and then it starts with the cut of the input to a FIFO. This goes to a TR, and then after the TR we have parallelization using autosplit, and so on and so forth. Then we have 4 copies of this TR and 4 copies of the sort, and so on and so forth. And we have more splits, and we also have the eager the eager commands, which are the buffering commands, as we mentioned before. Then we wait until the data flow graph is over, we remove the FIFOs, and then we're done. So let's now look a little bit at our evaluation. So first of all, we have a set of expert-written scripts that we've taken from GitHub and the literature. And on those, we run those on 4 configurations. So first of all, we run it with PaSh, a sequential configuration. Then we run it with a configuration where there is no runtime support. Then with a configuration where the eager is blocking, as we showed in the runtime section. Then with a configuration where PaSh has no split. And then with a complete PaSh configuration. And we can see that the PaSh configuration actually outperforms all other configurations and gives significant speedups, except for the case of shorter scripts, which actually does not need any buffering. So the no runtime support configuration is actually better. Top N is actually the script that we showed in the beginning of the presentation. And the speedups are actually significant. So for the 16-width case, against the PaSh line, the complete PaSh with all the optimization gives 883 speedup compared to 593 of the no runtime support PaSh. Second, we have a set of pipelines taken from the wild that are created as solutions for the Unix 50 challenges. So here's a plot showing the speedups on blue and the sequential times on red. And blue here, the blue line is the mean speedup. And the configuration is PaSh with width 16. And as you can see, scripts, there are parallelizable scripts that PaSh manages to parallelize and achieve speedup for, and there are ones that are not parallelizable, for example, because they contain awk. And these scripts, you can see that PaSh does not actually significantly slow them down, but it rather keeps them almost in the same execution time as their sequential counterparts. An interesting anecdote is that PaSh awareness goes actually a very long way. So for script 26 that we have here, it was originally developed with a knock that duplicates the second column in the beginning of its line and then sorts the lines. But if you actually just sort them with the second column as a key and then keep the column that we need, then from executing it sequentially, we can actually execute it and get 8.1 speedup with PaSh. So finally, we will show a case study, some information from a case study that is a long weather analysis script that was taken from the Hadoop book. So this script actually contains several stages: data fetching, data preprocessing, cleanup, and filtering, and finally the calculating. And the Hadoop book only focuses on this part, which is actually about 100 lines of Java code and only 4 stages in a shell script pipeline. So we actually re-implemented this calculation as a shell script, and then we ran this whole script using BASH. And BASH, as you can see, the first part, which is only pre-processing, takes 33 minutes and 58 seconds for 5 years of weather analysis data. And the second part takes 10 minutes and 4 seconds. This is for 82 gigabytes of data that are 4 years of weather data. And if we execute the same thing with PaSh, with PaSh we can see that it speeds up the first part by almost 2 times for the preprocessing, and then the calculation part it speeds up by 12 times. And the combined speedup is about 252. But the important thing to note is that traditional parallelization frameworks do not focus at all on this first part. And this actually, in this case, has the biggest impact for execution time. In our paper, we actually have more evaluation that you can go check out if you want to. So to conclude, PaSh proposes a parallelizing compiler that takes a shell script and returns a parallel shell script that can be executed on top of the user standard shell. It also addresses extensibility issues by proposing a correspondence framework that is based on the study of many commands, including the full set of POSIX and GNU core utils. PaSh is open sourced and can be found in the link here. I finally want to close with the fact that there is a lot of recent research on the shell, enabling fresh perspectives on old problems. Let's rehabilitate the shell together. Thank you.